All right, we're now going to tackle the tower law. Your book calls this the one I'm going to state as the short tower law. I don't know that I have ever heard anyone call it the short tower law. I'm not saying it doesn't happen. I'm just saying I've never heard it. But suppose K, L, M are subfields of C, and K is contained in L is contained in M. Then the degree of M over K, that's the big extension, is the product of the degrees of M over L and L over K. Okay. So the big extension is here in green, and that's going to be the product of these intermediate extensions here, the degrees of the intermediate ones here. Green and green is not a good choice. Let's see, green and purple. All right, so that's what it says. Okay, so the dimension of M as a K vector space is the dimension of M as an L vector space times the dimension of L as a K vector space. Now, this is true even when you have infinity here, and even when they're not subfields of C, so there's various different types of infinity. And this is not a set theory class. Almost all of our extensions are going to be finite. We're never going to go to an infinite extension unless we want it for a counterexample, in which case we have some examples like transcendental ones. So almost all of our extensions are going to be finite. So I'm only going to do the proof in the finite case. But if you know cardinals, the same is true, but you have to invoke the use of cardinals in cardinal arithmetic, which we're not going to do. Okay, so proof, we assume all degrees are finite. It's just a simplifying assumption. Okay. I guess I didn't say it, did I, in the definition here? Let me just put an addendum real quick. The extension is finite. And that's a technical term. If L over K is finite, otherwise it's infinite. And again, we're not going to go into layers of infinity in this class. All right, so okay, we assume all degrees are finite, and then actually, sorry, let me scroll up one more time. Let me just remind you what we did in our motivating example. We had this tower of extensions, and we picked a basis for the first extension. That was this 1 and root 2 here. And then we picked a basis for the second extension. That was this, 1 4th root of 2. And we saw that when you multiplied them, you get a basis for the large extension. That's the proof. So let's carry that out. So suppose xi, I equals 1 to n, is a basis for L over K. All I'm saying is the degree is n, and that is a basis. And yj, j equals 1 to m, is a basis for m over L. And again, all this is saying is that I have an explicit basis, and this degree is m. Okay. All right, then what? Well, then let's consider the pairwise product of all of them. Consider xi, yj, where I ranges from 1 to n, I think I said, and then j ranges from 1 to m. Okay. Look at all of these pairwise products. All right, to show, consider this, and we claim this as a basis. To show this as a basis, we have to show that it is linearly independent and it spans. Okay, or we can show that every element of M is uniquely represented as a combination of these, and that's a little bit tricky. So, right, because we can express every element of L, or every of M as a unique representation over L, and then all of the elements of L as a unique representation over K. But then we have to like worry about, well, how does the mixing happen? So we're going to do just straightforward argument by showing this collection is linearly independent and it spans. Okay, and that will be equivalent to unique representation. So suppose that a sum of these guys, I'm going to ignore the subscripts at this point with the understanding that the I index ranges from 1 to n and the j index ranges from 1 to m. Suppose that you have a linear dependence of them over k. We claim it as a basis. Let me just be even more precise here for m over k. That's the thing that we're after, right? We want to show that the degree of m over k is the product of them. So there's m times n things here, so we want this guy to be a basis, and then that will do it. So suppose this is a linear dependence over k. So with, of course, kij in k for all ij. Like again, the obvious range here for I and j. Then what? Well, we can kind of rearrange this. We can rewrite our sum as the following. Scroll down a little bit here. I'm going to put the 0 on the left. We can first, for each j, sum over I. So we have sum over j, sum over I, kij, xi. The sums involved are finite, so you can interchange the order in which you add. You can add over I first, or j, or any combination thereof. We're using that the sums are finite here. Okay, so this is 0. But these guys here are k-linear combination of the x's, and the x's were a basis for L over k. So this element's in L. So we have a linear combination, an L linear combination of the basis yj being 0. Well, since it's a basis, that must mean that all of the coefficients are 0. Remember, this is a basis for m over L. Okay? So thus all the coefficients are 0. All right, but now we have a k-linear combination of the basis for L over k being 0. Actually, we have a bunch of them. We have one for each I. But xi is a basis for L over k. So the fact that this linear combination is 0 tells us that all of our coefficients are 0. All of our coefficients are 0 is exactly what we want to show, right? What does it mean to be linear dependent? Well, if you have a combination of your guys you want to show are linear independent being 0, then all the coefficients must be 0. And we showed that. Cool. Now we have to show that it spans. Let me conclude that train of thought. Thus, this set xi yj over I and j is a linearly independent set. All right, what's next? Well, we have to show it spans. So take any z in M. We will write it as a k, I'm just going to write LC, k linear combination of xi yj. Right? All right, well, firstly, we know that the yj are a basis for M over L. Oops, that should be a capital L. Thus, by definition, a basis is something as a spanning set. There exists coefficients Lj and L such that Z is a sum on J, Lj, Yj. Again, I'm abusing notation here and not writing the range. Each Lj is in L, and the Xi are a basis for L over K. So for each J, there is a collection of coefficients Kij such that Lj is a sum on I of Kij xi, right? Each one of our coefficients in L, we use the fact that L is a K vector space to write them as in terms of the x's. Thus, Z, which is the sum on J, Lj, Yj, is then the sum on J, sum on I, Kij, xi, just substituting that in. But like before, it doesn't matter the order in which we add, all our sums are finite. We can do that. So any Z and M is a linear combination of our proposed basis. Thus, our proposed basis spans. And since it's a linearly independent spanning set, it's a basis. So what do we conclude? Well, we conclude then that the dimension of M over K, or the degree of M over K, is the size of this basis. This is cardinality bars. And the size of that basis is certainly M times N, because you have M choices for X, or N choices for X, and then M choices for Y. But N was the degree of L over K, and M was the degree of M over L. And of course, this is just multiplication of numbers. So it doesn't matter the order in which we do that. And that's what we wanted to show. All right, so it's a little bit long because we have to dig into some of the nitty-gritty details, but the core of the proof was exactly that motivating example. We take a basis just to, alleviate some of the symbols. We took a basis, where is it? Here it is. We took a basis for the small extension, that's the second sentence. Then we took and in the second sentence, we also took a basis for the second extension in the tower. So K over L and then, or L over K and then M over L. And then we multiplied them. And in the example that we did, it was obvious that it was a basis because we could see it. But in this case, it's not so clear. So we actually had to go through the work. But the heart of the proof is knowing to multiply them. And after that, it's just some computation.